Alright, today we're going to look at Newton's identity for cubic and higher degree polynomials. In cubic equation, you're going to have more coefficient, for the terms. Now always start with, for the cubic, always start with leading coefficient of 1, right? Because if it's not 1, you can divide by that coefficient and make it 1. And the equation still have the same solution, same roots. Alright, so here we have B, C, D constants, and we try to figure it out without solving the equation. Try to find out different polynomial of the roots, like the power, and then sum of the powers. Right. So first of all, we know that for cubic we're gonna have 3 roots. One of them is real. The other 2 could be real, could be complex numbers, right? So let RST be the roots. This polynomial here on the left hand side is the original polynomial. On the right hand side, because we have the root, so it must be equivalent to this, product. If you expand it out on the right hand side, right, notice that the coefficient, x squared and x must be identical to the corresponding terms here. So in other words, this coefficient must equal to b, right, with the negative sign here, and here must equal to c. This whole thing here with negative sign must equal to d, right? So in other words, r plus s plus t equal negative b, rs pairwise equal c, and then the multiplication of all 3 equal negative d, right? So now you may have to think why that is the case, right? Can we generalize for the higher degree? What happened to the degree 4 when we have 4 roots, or degree n where we have n roots, right? So let's look at that. So for the degree nth degree, right, in terms of 1, so we're gonna have an other constant with n other constants, and then we have n roots, right? In this case, we're gonna say r1 to rn is n roots. And again, when you expand this out, right, so expand the right hand side and then compare the coefficient here with different degree. Let's choose, for example, n minus 1 degree, right? And the coefficient is b1. For the right hand side, in order to have n minus 1 degree of x, for each term here, because there's always like a cross product here, right? So you have to choose n minus 1x, and you choose one constant term. In other words, from the n roots, you're going to choose 1 for each term, and total there's going to be n choices, right? So what you end up with here is you end up with minus r1 plus r2 plus rn for the right hand side, and then you have x n minus 1 term, right? Xn term, and for the rest of it, you're going to in general, for the n minus k degree, there's n choose k ways of choosing some combination of these rules. And notice that when you can verify the following conclusion, right? All right, so there's a typo here. This should be b3 and this negative sign, and the sign is alternating, okay? And negative plus negative, and then as n, depending on the n is even or odd, we have different numbers. Notice that on the left hand side, right? On the left hand side, we notice that each term is symmetrical in the roots. So here, this is kind of the sum of a single roots, right? Here's the sum of multiplication of two roots, right? Pairwise. Here is every 3 in a group, right? So how many terms here? In here, there must be n choose 3 terms, right? And here there must be n choose 2 terms. Here is n choose 1 terms, in which case equal to n, right? Here is pairwise, it's going to be n choose 2. And similarly, here there's only 1 term because it's n choose n, right? Which is 1. How many terms are there, right? So we're going to use some notation here. So we notice that these polynomials, first of all, the left hand side, they're polynomials in the roots, in the Ri's, right? So R1, Rn. And also each term is symmetrical in Ri. So for example, everything is exchangeable, right? So you're going to enumerate all possible combination of it, of either pairwise or 3 out of n or k out of n, right? So we call them an elementary symmetric polynomial, right? So this is elementary symmetric polynomial. So let's say for degree 5, if you have 5 roots, x1, x2, x3, x4, and x5. And what is sigma 1 here in that case? Is sigma 1, notice that is elementary. This would be the first one would be sigma 1. This one would be sigma 2, sigma 3, and this would be sigma m. Okay? So for the 5, sigma 1 would mean what? You choose 1 and then you add them up. It's going to be sum of x1 plus x2, s3, x4 plus x5. So what is sigma 2? Pairwise. So for the pairwise, it's going to be 5 choose 2 possible pairs, right? So you can add them up. So x1, x2, right? Plus, it's going to be 10 of them. I'm not going to write them out, but you would know that you compare every possible pairs, right? x3 plus x1, x4 plus x1, x5, and so on and so forth, right? So, and sigma 5 is going to be this. What is sigma 6? You try to choose 6 out of 5, which is not possible. By convention, we say that sigma 6 equal to 0. In other words, sigma k equals 0 if k is greater than the degree n. In this case, n is 5, right? Yeah, this is like n equal 5 case. All right. So this is a very important annotation, sigma k. Now, so here comes the main conclusion of the recurrence relationship, which is Newton's identity. That is the Sk. Now recall that Sn is actually the sum, right, of all the root like r xi to the nth power, right? For the nth power of all the roots, you add it up. Now we have this recurrence of the sk, the kth power sum, sk minus 1 and sk minus 2, and versus s1. Remember that s0, s0 usually is just add up to the zeroth power, which is in this case, for the roots there would be n, right? There are n of them, right? That's important to know for the degree n. Okay, so we're not going to prove this, but one thing when you think about it, for example, for degree n, right? So if k is greater than n, this term will go away, right? So otherwise, if it's smaller, you're going to use this formula here. The sign here is alternating, right? Sigma is elementary polynomial here of the roots. This is the powers. This is like the sum of the powers, right? So the actual proof is actually very intuitively, it's very easy to think about if k is bigger case, right? For example, for the degree 3, right? For example, this degree 3, right? So n equals 3, right? So if k equal 4, for example, let's write it out. So plug in S4. So S4 minus S3, right? Sigma 1 plus S2, because k equals 4, right? Sigma 2, and then minus S1 sigma 3, and then plus -1 to the fourth power times 4 and sigma 4, right? K equal to 4 equal 0. But notice that when k equal to 4, sigma 4 is equal to 0. So these terms goes away. So what I have here is only this part, right? So S4. Now we're gonna see what is the intuitive, why that is the case, why that the whole thing here equal to 0, right? So let's recall that n equals 3. The original equation is x third power plus bx squared plus cx plus d equals 0, right? And the sigma 1, we know that is equal negative b, sigma 2 equals c, and the sigma 3 equal negative d, right? So when you plug in this, so sigma 1, sigma 2, 6, 3, right? So we say that S4, right, minus S3, which is plus B, S3, plus C, S2, plus, and then here is S1, right? S1, negative cancel, and then it becomes ds1 equals 0. What is the relationship between this equation 1 and this equation 2? Now notice that for any roots, if you satisfy equation 1, you multiply x by both sides. What do you get? You get x4 plus b x third plus c x squared plus d x equal 0, right? This, okay? And then of course, if there are 4 roots, right, you can repeat this equation 4 times, right? So let's try that. All right, and then for example, this is xi and for the roots you set it as this, right? But then if you do the four roots, you add them together, this still works. And notice that by definition the sum of four roots of xi to the first power would be s4. So you get s4 plus b s3 plus 3c s2 plus d s1 equal to 0. This is exactly what we have, right? But for k smaller than 3, we're not going to prove this equation, right? Let's take it as a fact. All right, so let's work out some example here, right? So this is just a recap of what is Newton's identity. And here we just plug in some special cases, right? This is just some special cases here. I just plug in for the initial terms, right? S2, S3, yeah. And in the cubic polynomial, we have S4. You know, we know that that is what we derived here earlier, right? Yeah. Anyway, now let's look at an example. For this quadratic equation, cubic equation, right? It's 3 roots, right? So what is S4? So for example, if the 3 roots are x1, x2, x3, we try to find out what is the sum of that. What is S4? All right. We can just plug in to the equation. But here notice that what is a b c d here? The x to the third plus bx squared plus cx plus d is generic equation. But in this case, we don't have the s squared term. So in other words, in this case, b equals 0, right? C equals 6, and d equal negative 20, right? So what is sigma 1, sigma 2, and sigma 3, right? So from the early on, we know that sigma 1, right? So sigma 1 equal negative b, in this case is 0. So sigma 2 is equal c, which is 6, and sigma 3 would equal to negative d, which is d itself is negative 20, because it's negative 20, so sigma 3 is 20. What is sigma 4? Because remember, the degree 3, sigma 4 would be 0, right? Because it's greater than 4. Now, given that, and given the recurrence relationship here, we can just plug in, right? What is S1? S1 equals sigma 1. Sigma in this case is 0. So S1 all right, so S1 equals 0. Okay, what is S2? So S2 here, we plug in this, is S2 equal to, you move this 2 to the right hand side, S1 sigma 1 minus 2 sigma 2. So S2 equal S1 sigma 1 minus 2 sigma 2. Alright? Of course, S1 equal to 0. This goes away. Right? So S1 and minus 2 sigma 2. Sigma 2 is 6. So this is negative 12. Right? And then what is S3? Right. Oh, sorry. S3. Right. S3, you're going to plug in here. Right? So, and then move everything here to the right hand side, is equal S2, yeah, sigma 1 minus S1 and sigma 2, right? And plus 3 sigma 3, right? Yeah. So and then you plug in the results earlier. This would be, x2 is -12, sigma would be 0, right? Minus s1, that would be 0, plus 3, sigma 3 is 20. That gives us 60, right? Now what is x4, right? So x4 we plug in, right? As for earlier, we said that x4, we have this relationship here, right? So in other words, for the higher degree, s4 plus b s3 plus c s2 plus d s1 equal 0, right? In our case, b equals 0, so this goes away, yeah. And then s4, so s4 and c s2, so s4 plus c is 6, s2 is -12, plus ds1, d is -20, s1 is 0, so equals 0, so s4 equal 72, right? So s4 equal 72. That's our answer. Now let's try to verify this equation. So we know that s4 is 72. Now notice that there's one root 2 with x equal to 2. When x equal to 2, you plug in, this is 8 plus 12 minus 20 equals 0. So x2 is one solution. So one root is 2. How about the other two roots? Since you know 2 is the root, there must be a factor x minus 2 on the left hand side, right? So we're going to try to factor this. Minus 20 equal x minus 2 times something, right? And then of course x squared here. And then the way to do it is when you try to expand it out, that would be x to the third minus 2x squared here. But then you need to get rid of this 2x squared, right? So you need to plus 2x. So 2x times this, you get 2x squared minus 4x, right? This one, if you multiply this term, you're gonna get that, and this cancels, and you have like the 4, but then you need plus 6, so you need to plus 10x here, right, in order to get plus 6. So here you have plus 10, but for the 10, if you multiply this, x minus 2 will be minus 20, exactly what we have. So this one is a factor and equal to 0. So how to solve x squared plus 2x plus 10 equals 0? Complete the square, which is x plus 1 squared plus 9 equals 0, or x plus 1 squared equal -9. So it's a complex number. X equal -1 plus minus 3i. Okay, so we have 3 roots. What are they? We have 2, right? 1 plus 3i, -1 minus 3i, right? X squared, what is the square? This will be 4, right? X to the 4th, and then this will be 16, right? 2 to the 4th power. And here, when you square it, you become -1 squared, right? So that becomes -9 plus 1, -8 minus 6i. This will be -8 plus 60i, right? If you square it again, that will equal -8 squared, 64, plus 2 times 8 times 6i and plus negative 6i squared. So that will be equal 64. This would be negative 36, and this would be 96i, right? So that is 28 plus 96i. 28 plus 96i. 28 minus 96i. Okay? So what is S2 here? You add everything up together. So S2 would equal to, when you add them together, this imaginary part cancels, right? And this negative 16 plus 4, negative 16 plus 4 is negative 12. All right. So what is S4? S4, you add these cancels. 28 plus 28 is 56 plus 16, that's equals 72. This is exactly what we get from the formula. Earlier, S2 equal negative 12, right? So S2 equal negative 12. All right, we verified that. All right, so that's it for today. There are a lot of contents. Please go back and review the slides. All right, thank you.